What is up, crew?
What's up?
Got me, and you got Ben,
Yeah.
and we're going to be working through something that both of us have been interested in for a while now, at least I have in particular.
Yes.
MIT does a pretty good job of sharing all their coursework. So we're going to go and share our screen for the remaining duration of this whole video, because we're going to be working through the coursework that MIT shows or shares about problem sets and lectures for their distributed systems class. So we're going to switch over to screen share. We'll do the whole window. And we will go over to the course. So for those of you who don't have the course, we'll drop this in the video chat if you guys are curious to follow along. But basically, the last time this course is offered, it gets offered, I think, every spring semester. So we're going to go click through to the information or schedule for the course. And you can see what kind of a enormous task me and Ben are taking on right now.
Yep.
We'll see how far we get.
Probably not very far.
Probably not that far, but we'll see. We'll see.
We'll see.
First of all, I think we need to get Go installed, but even before we get Go installed, let's just read lecture 1.
Sure.
I mean, as a preface for getting into the labs, which are the problem sets of the course, you can see that it's a full semester's worth. I think the readings are going to be pretty brutal. And if we do an episode 2, which I hope we do, is that we could do the readings hypothetically outside of the live stream.
Yeah, beforehand.
And then come meet up and talk about them.
Yeah.
Whether they're boring, whether they have any bearing on our personal careers as software engineers or not.
Right.
Want to check out lecture 1?
Sure. Introduction.
Cool. So this is very well structured, visually rich. MIT.
Visually rich, hypertext markup. Just plain text, actually.
Yeah. So the lectures. Why? Well, let's check out the top. What is a distributed system, Ben?
It's multiple cooperating computers, big databases, peer-to-peer file sharing, MapReduce, DNS. Lots of critical infrastructure is distributed.
So why distribute software?
To connect physically separate entities, to achieve security via isolation, to tolerate faults via replication, to scale up throughput via parallel CPUs, mem, disk, net, etc.
Wow, that sounds extremely valuable.
It is extremely valuable.
But it's
complex. Many concurrent parts must cope with potential and partial failure, tricky to realize performance potential.
And why on God's earth should we take this course, Ben?
Because it's interesting. There are hard problems, powerful solutions used by real systems. It's driven by the rise of big websites and is an active research area. Lots of progress, plus big unsolved problems. Hands-on, you'll build serious systems in the labs.
So for our audience, of which there might be 0 at the moment,
Sure.
Have you taken this course ever before?
I have not taken this course. I think I probably took a distributed systems course a long time ago in college, but I'm sure that the landscape is very different today
Okay.
than it was.
Okay. So I have never taken this course. I've taken, well, I didn't do my undergrad in CS like you. I took some CS classes and took a couple of upper division classes, but did not take distributed systems.
Yeah.
I know you've been on the show previously, and we talked a little bit about your background, but at Checkr, do you guys do any distributed systems types of problems that you guys have to tackle?
Well, I mean, yeah, like we have a lot of systems that all kind of work together. We do a lot of asynchronous processing of events that then do some piece of work and then report back to various, oh shoot.
We can change the power settings when I do that real quick.
I would say yes, we do a lot of different various.
I'm not sure it's actually charging.
It's not. Various different distributed systems.
Is there a switch or something? We can plug it directly down here. There's another extension cable.
It's easy.
Cool.
Oh, there we go.
But basically, all the problems you're describing existing with distributed systems over here, or that are in the lecture notes here, are relevant to what you're doing on a day-to-day basis.
Absolutely, it's relevant to, I'm sure, a lot of companies. If you just have one server serving traffic, that's a pretty rare scenario in today's world. So
For sure.
I would say whatever you do, ultimately, you're going to be dealing with some form of distributed systems.
Whether you are writing the software backing it or not, you will be evaluating software
you will be choosing,
possibly.
Yep, you will
other
be choosing software that is a distributed system and taking in pros and cons.
Cool,
So,
cool.
Yeah.
So the faculty who are not present for our live stream, unfortunately, Robert Morris, who I believe has been teaching this course for a while. He's really famous for being the creator of the first worm, I think. Robert Morris, computer scientist? Computer virus. That's what it auto-completed.
And I think he helped found YC.
Oh, really? Okay.
I believe so.
So he's known, I mean, I think his father was a super famous computer scientist, but
yeah,
pretty well-known MIT faculty member. Franz Kaschuk. Sounds Eastern European. He's Dutch.
Dutch.
Okay. His advisor was Tannenbaum. I think that's the guy who wrote the Dragons compiler book. Maybe.
Oh, wow.
Also Dutch, or lives in the Netherlands. All right, whatever. They look cool. We're just going to be
I think they know what they're talking about.
Probably. And all these poor underpaid PhD students.
Yeah.
Poor guys and girls. Course components. Lectures, readings, 2 exams, labs, final project. The lectures are big ideas, paper discussion, and labs. This sounds like a pretty cool class.
It does sound like a pretty cool class.
Readings are probably going to be pretty heavy duty. Research papers. The papers illustrate key ideas and important details. So one of the things we'll do while we're walking through this course is there's kind of a particular way to read academic papers, which involves reading the abstract, then reading the abstract again, and then going to the very end of the paper and reading the discussion, and then going back and reading the abstract. Because like usually these things are super inscrutable, and then you go talk to your professor, which neither of us have done grad programs, so we haven't had the opportunity to really do that. But reading papers is a skill in of itself, so maybe we'll do some of that on the live versus out of band when we come back and discuss about the papers.
Yep.
Midterm. This is the beauty of not actually taking a class, is we don't need to fucking do a test.
Yeah, we don't need to study for any tests.
Lab goals, deeper blah blah. We know this. So there's 4 labs, and these are the problem sets of the course. And it doesn't sound like much, but these are probably pretty large coding-based exercises.
Yep.
So MapReduce, I think a lot of our audience might be familiar with it. If we've got anybody, not yet.
Okay.
MapReduce, do you mind describing, just without having taken this course, what your intuitive understanding of MapReduce is?
My intuitive understanding of what MapReduce is, it's a way of breaking down a problem to use basically 2 functions, a map function and a reduce function. The map function maps over a bunch of data and then it basically determines something about that data, and then the output of that function gets fed into a bunch of reduce functions, which then take those pieces of data and then reduce them to somehow, like let's say you want a total count of words in a text file or something. And basically, breaking it down in these 2 ways, it allows you to then run the map functions on different parts of the input on different computers. So like you can then now scale this basically as large as you want. You can run 1,000,000 map functions, and then you can run 1,000 reduce functions across many different computers and get an answer more quickly, is my understanding of what MapReduce is.
Right on. I mean, that's very generally my understanding as well. We'll probably learn a lot.
We'll probably learn
We'll
a
probably
lot.
learn how to exactly describe it,
Mhm.
as I have no idea how to exactly describe it from the papers. But replication for fault tolerance using Raft. So Raft, I believe, is a pretty recent academic development. One of the big problems in distributed systems is consensus building, where you have all of these different computers, and all of them cannot know what each of the other ones know exactly in real time. So if, for example, one computer in a network of computers loses internet connectivity, and so the other computers can't see it, or it can't see the other ones, then you need some way of building consensus among your different computers independently about what is the correct state of the universe.
Right.
So Raft is a newer version, and the best in state of the art when it comes to consensus building in distributed systems. So people know about Paxos. Paxos is the predecessor to Raft in terms of the name of an algorithm that does this. Fault-tolerant key-value store, sharded key-value stores. They sound kind of like Redis and like how to build Redis.
Yep.
Or whatever the Amazon, Google, Azure equivalents are. Yeah. Optional final project. We're not. Well, let's see. Let's not get our hopes up.
Yeah.
Lab grades. Don't even need to worry about that.
Nope.
Although I think the labs are tests, so you write your code to see if they pass tests. So in terms of grades,
cool.
we can just say, did we get all the tests to pass?
Yeah.
Main topics. Okay. You want to take a crack?
Main topics. This is a course about infrastructure to be used by applications, about abstractions that hide distribution from applications. 3 big kinds of abstractions are storage, communication, computation.
So
not sure if there's
missing visual. Yeah.
Yeah. So this is why you use something a little more than text to write your documents. A couple of topics come up repeatedly. Topic, implementation, RPC, threads, concurrency control. So this is like, what is the underlying thing doing the distribution?
Yeah, we're going to come across these acronyms like RPC.
Yeah.
And as soon as we encounter them, I think it would be helpful for even just our mutual understanding of the topic.
Yeah.
To
RPC, remote procedure call.
Remote procedure call. There's definitely a massive Wikipedia article about this.
So remote procedure call is when a computer program causes a procedure subroutine to execute in a different address space.
Commonly on even another computer.
Yeah, so if you think about a remote procedure call, it's just calling a function, but that function isn't like running in your code base, or maybe it's running in your code base, but it's not running on that particular computer, it's running on another computer. And you send the request to that computer, and that request then runs that function and then returns the results to the computer that originally called it. So it's remote.
So most all web APIs are examples of
a type of RPC, yeah. So if you accept, like, let's say you request JSON from your web server from your front end, that's a type of RPC, remote procedure call.
Yeah, you rarely see that acronym in particular show up in web programming.
Yeah, people don't think about it in web programming like that, but it definitely is a type of RPC.
Oh, for sure. Interacting with databases too, like inserts, deletes, or updates, or reads.
Yep, they're basically RPCs that use some kind of contract for how you talk about calling these functions.
So yeah, threads, concurrency control, those are like massive topics. I think we should move on.
Yeah. Topic performance. The dream, scalable throughput. N servers equals N total throughput by a parallel CPU disk net. So handling more load only requires buying more computers.
That's a pretty ideal.
Yeah, so this is like the perfect in a perfect world.
That's the holy grail that we're trying to achieve in the study of distributed computing.
Yep. But scaling gets harder as N grows. Load imbalance, stragglers, non-parallelizable code. So in this case, this would be code that you can't easily break down and distribute to multiple computers. So you're stuck with, there's basically a ceiling for how fast that one computer can go.
Mm-hmm.
bottlenecks from shared resources like network overhead, stuff like that. Topic, fault tolerance. So thousands of servers is pretty complex, and there is always something that's going to break at some point somewhere. And we'd like to hide these failures from the application. So the application, as far as it's concerned, doesn't really care if something breaks or not. It gets back the data it wants, or it gets back some kind of uniform error message or something. So the application doesn't have to worry about the implementation details. We often want availability. App can keep using its data despite failures, and durability. App's data will come back to life when failures are repaired. Big idea, replicated servers. If one server crashes, the client can just proceed to the next server, kind of load balanced.
For sure. We'll do Passover style.
Yeah.
Okay.
Yeah.
I mean, all this makes sense. We don't have an audience yet, so we can just keep going and answer questions that each of us have for each other. Topic is of consistency. General purpose infrastructure needs well-defined behavior. For example, getting a key yields a value from the most recent put of that key. So achieving good behavior is hard. When you have replica servers, it's hard to keep them identical. Clients may crash midway through a multi-step update. Servers crash at awkward moments, for example, after executing but before replying. Network may make live servers look dead. And there's this risk of a split brain scenario where you have one or more servers that have different understandings of the universe. Consistency and performance are enemies. Consistency requires communication, for example, to get the latest put of the value. Strong consistency often leads to slow systems. And this is a very common problem in practice. People often in businesses make sacrifices to have their systems be moderately fast or blazingly fast, as some salespeople call them.
Sure.
MongoDB IPO'd this week. But that has some really, really, really serious trade-offs and sacrifices consistency.
It's good to be aware of the trade-offs in making decisions.
Which is why we're taking this course. High performance often imposes weak consistency on applications. People have pursued many design points in the spectrum. That is for sure true. So relevant to this first lab, case study of MapReduce. Let's talk about MapReduce as a case study. MapReduce is a good illustration of the distributed systems course main topics, and it's the focus of lab 1. We're probably like blazing through this lecture in comparison to what it was like sitting in the lecture hall.
Well, I don't know how long the lectures were. Probably an hour.
We're about halfway through. So we're blazing. We're going at like 50% faster speed. So you mind sharing the MapReduce overview?
MapReduce overview, context. So multi-hour computations on multi-terabyte data sets. For example, analysis of a graph structure of crawled web pages. This kind of algorithm came out of Google precisely for this reason. Overall goal, non-specialist programmers can easily split data processing over many servers with reasonable efficiency. Programmer defines map and reduce functions as sequential code and often fairly simple functions. MR runs the functions on thousands of machines with huge inputs and hides details of distribution. So really, all a programmer needs to know is I have input, that gets sent to a map function, that output gets sent to a reduce function, that reduce function gives me an answer. And it's really easy to break down the problem, even if you want to run that on a terabyte of data and 1,000 machines. Abstract view of MapReduce. This is what I just said. Input goes to map like that. Input 2 goes to map. And then the output of all of this goes into reduce. Intermediate data, each map call is a task. MapReduce gathers all the intermediate data and then passes them on to the reduce call. The final output is a set of key values from reduce stored in output files. So here's an example of word count. So like, let's say the input is thousands of text files, let's say a terabyte of data. The map takes the input, it splits the value into words. For each word, it's going to emit the word and the character 1. And then the reduce function is going to take the output of all of these map functions. So in this example, let's say the word is the, and then a list of all the ones that was emitted. And then this reduce function is just going to give you the length of that list. So you're going to end up with basically the word, the, and the number of times it appeared in the text.
Mm-hmm. So I remember from possibly my first programming class, which was about functional programming, about the global functions named map and reduce. I was using a language in my first programming language class called, or my first computer science class called standard ML, which is a functional programming language.
Yep.
But map and reduce were functions built into the language that do exactly what's being described here.
Yep.
The key here being that these map operations and reduce operations can be performed across a bunch of different computers.
Yeah, so I think it takes the same like concept of like if you think about a map function and you call that on an array, it's basically that concept, but the framework will abstract the details of like, let's say the array is huge and mapping over it sequentially will take forever. It'll abstract the details of, I want to split this up into bite-sized chunks for 1,000 different computers. And the same with reduce. You want to split this up and run it on 1,000 different computers. It'll abstract that away so you don't have to think about it. But this is anyone with a little bit of understanding can approach and understand what's going on.
For sure.
Which is kind of crazy. I mean, if you think about computers, computer science as a goal is about abstraction, like making it easy for people to kind of get things done by abstracting the harder things. Like that's kind of what you see here.
For sure. So MapReduce hides many painful details. You didn't already mention this, right?
No, that's where I stopped. Yeah,
okay.
Yeah, that's good.
Starting, I was trying to help co-promote the Facebook and Twitter links. At this point, still 0. MapReduce hides many painful details, starting software on servers. That in and of itself is a pain in the dick.
Yep.
Tracking which tasks are done. Data movement, so moving data between the different computers that are performing your MapReduce task.
Yep.
And then recovering from failures. Yeah, that is also really painful.
Yep.
MapReduce scales well. N computers get you N big O of N throughput, or big O. I might be using big O wrong there. Assuming M and R are greater than or equal to N, your number of maps and reduces are bigger than the number of computers you got.
Yep.
Scales well for that case. Maps can run in parallel since they don't interact with each other. Same for reduces.
Yep.
So you can get more throughput by buying more computers, rather than special purpose efficient parallelizations of each application. Computers are cheaper than programmers. That is for sure true.
That is absolutely true.
Buy Amazon stock. Buy Microsoft stock. Buy Google stock. We'll all be rich. What will likely limit the performance? We care since that's the thing to optimize. CPU, memory, disk, network. These are all configurable things that you can pay for in your computers before you go and tackle this problem. In 2004, authors were limited by quote-unquote network cross-section bandwidth. So we're missing an image here, but servers with a bunch of network switches or routers between them introduced bandwidth cost in transferring data between any two computers. So a map task that might be handing work off, its outputted data off to a reducer task on a different computer, that was the inhibitor for using the MapReduce approach.
Yep.
Note that all data goes over the network during a MapReduce shuffle.
Yep.
Just what we described.
Yep.
Paper's root switch, 100 to 200 gigabits per second. 1800 machines, so 55 megabits per second per machine. Small, for example, much less than disk or RAM speed. So
yeah. So they cared about minimizing movement of data over the network. So I think what this means is the MapReduce framework. When you give it the data that you eventually want to analyze, it puts it on several different machines in the file systems, or in Hadoop's example, HDFS. And then the map functions actually get sent to the computers where that function is going to get run. So it's actually, you're not moving the data to the map function, you're moving the map function to the data. So you don't have to move a terabyte of data to run the map functions. You just kind of send out the functions you want to run to the framework runs it and reports back. So that's, I think, what it's trying to, it's minimizing the movement of data over the network.
Makes sense.
Yeah.
More details from the original MapReduce paper, which, by the way, I don't know if it's been mentioned yet in the lecture notes, but it came out of Google as opposed to professor or academics.
Yep.
Research institution, where they came up with this solution for coping with this very issue of having massive quantities of data,
right,
and having to figure out how to scale out parallelizably and performantly. So in a Hadoop, or excuse me, in a MapReduce cluster, there's a master computer which hands off tasks to workers. And it is in charge of remembering where data is being handed off from worker to worker. Yep. We're going to use these variable names M and R to refer to the number of map tasks and the number of reduced tasks. Input stored in Google File System, or GFS, which is a Google innovation to be able to store data across computers.
Yep.
It looks like there's 3 copies of each map input file. Okay. All computers run both GFS and MapReduce workers, so they have their file system and
yep.
Are able of handling map and reduce tasks. So there are way more input tasks than the workers, so the master node must give a map task to each worker, and it hands out new tasks as old ones finish. So it queues up all the work, and then the workers are responsible for pinging the master and notifying the master of its state so that the master can give it new work if it doesn't have anything yet. So map worker hashes intermediate keys into reduced partitions on its local disk. So when a map task gets completed by a worker, it gets stored on its. I'm unclear on what partitions refers to here, but we'll find. It says local disk. So
yeah, so I think what it's trying to do here is the result of the map function needs to get bucketed by the number of reduced partitions that you set ahead of time. So like, I think in general, there's going to be less reduce functions that run than map workers. Like you could have 1,000 map workers, but then only 100 reducers, I think. And then during the map phase, all the results from all your map workers need to get ahead of time split up then into 100 different partitions. And I think that's what it's talking about here. So then you have to wait for all the maps to finish and everything gets partitioned for the reduce phase to start.
That seems like one area where there's performance optimization that can happen.
Yeah.
So if the master tells reducers to fetch intermediate data partitions from map workers, reduce workers write the final output to GFS, 1 file per reduce task.
Yeah.
Okay. And maybe there's a final reduce which collects all those.
Sure. Yeah.
How does detailed design reduce effect of the slow network? Detailed design, we haven't covered that yet for show. Map input is read from GFS replica on local disk, not over the network. So they eliminate the round trip time of refetching map output to be processed for reduce input. Intermediate data goes over network just once. Map worker writes to local disk, not Google File System. Intermediate data partitioned into files holding many keys. Okay. Big network transfers are more efficient. So it's only at intermediate steps in the map task and the reduce task across the cluster that any big network file transfers happen. So it minimizes a lot of network chatter.
Yeah.
So how do they get good load balancing? Critical to scaling, bad for n-1 servers to wait for one to finish. Makes sense. Some tasks likely take longer than others. That also makes sense.
Yeah.
Many more tasks than workers. So you try splitting it up into smaller atomic pieces so there's no single big chunks that are clogging things up.
Yeah.
Master hands out new tasks to workers who finish previous tasks. Covered that. No task is so big it dominates completion time. Cover that. Faster servers do more work than slower ones. Finish about the same time. Okay, yeah, that makes sense. Breaking them up, break up your there's probably a variable map input size that you can configure depending on how your MapReduce implementation is.
Yep.
What about fault tolerance? Oh, we're almost done. We got 2 more sections, looks like. Once we're wrapped on this, though, I'll go back to the schedule and see what else remains about the day one. There's the actual MapReduce paper, which is a PDF.
Yep.
Which was the one published by Google. Jeff Dean, the most famous computer scientist possibly ever.
Possibly.
There's a bunch of never mind. The lab, which we'll take a look at, and which actually involves some coding.
Yep.
I've looked at this already, and some of the information they're giving is stuff that we don't need to cover, like how to get Git installed and get a hold of the source code. Hopefully in the time that we've got remaining, we'll be able to finish these notes, possibly take a quick look at the paper, and take another look at the lab instructions.
Yep.
We've already got the code ready. We got our trigger finger.
Yeah.
So it'd be cool to be able to, run some code and see whether the tests fail for the lab.
Yeah, totally.
But
I don't have Go set up, so
okay, that might be an adventure in and of itself.
Yeah.
So I think it's pretty straightforward. It's a little bit harder than Node, for example, or Rails, but once we've got it set up, it'll be good.
Okay.
Fault tolerance. What if a server crashes during a MapReduce job? How do we hide failures is a huge part of the ease of programming. Why not restart the whole job from the beginning? Well, that sounds expensive.
Yeah.
MapReduce reruns just the failed ones, failed maps and reduces. MapReduce requires them to be pure functions.
Yeah.
They don't keep state across calls. They don't read or write files other than expected inputs or outputs. There's no hidden communication among tasks, so re-execution yields the same output.
Yep.
Code. The requirement for pure functions is just a major limitation of MapReduce compared to other parallel programming schemes, but it's critical to MapReduce's simplicity. So I'm not totally sure what they're meaning here by pure functions. Maybe just that there's no I/O where state gets persisted.
Yeah. So pure functions is like I don't know the academic definition, but I think it means like given input, you get the exact same output, and there's no like state or side effects. So like it doesn't like talk to a database. It doesn't set a session or anything. It's just like you get input, and you do something, get the output.
So it doesn't even look at a clock, for example.
It wouldn't. Yeah, it doesn't even look at like
that would be input that would need to be provided a priori.
Yeah, I mean, unless you're emitting random data for some reason. But even then, that doesn't sound like a pure function to me, because that's dependent on some other variable.
Mm-hmm. Cool. So we got. Oh wait, we were just there.
Yeah.
So yeah, don't keep state across calls. Don't read or write files. No hidden communication.
Yep.
Yeah. So when a worker crashes, this is like not super mind-blowing stuff. This is not living up to MIT's reputation of being unbelievably hard to understand.
It's pretty straightforward. I mean, I think this is why MapReduce like really took over the past 10 or 15 years of computation, is because it's like pretty simple for people to understand.
I mean, on the other hand, are you aware of using MapReduce on a regular basis in your work at Checkr?
We at Checkr don't use MapReduce or HDFS. Certainly at previous companies we have, but at this point, I think probably smaller startups have moved on to other systems than MapReduce.
So this has been my experience too, 100%.
Yeah.
Do you have any of your own hypotheses about why startups in particular are like, wow, this is not worth our time?
Yeah, I don't know. I think ultimately, so MapReduce is simple. So if you look at like this example, like this word count is a simple, like it's simple for a programmer to understand, but it doesn't allow the business to get value out of its data as readily, someone that doesn't understand programming.
Yeah.
So I think the things that people have moved on to are things that expose SQL-like interfaces that might do like MapReduce type stuff under the hood,
Yeah.
but it's not really exposed. It's more like write a SQL query and either analysts can use it directly, finance people can use it directly, or you can hook it up to some user interface that knows how to create SQL queries, and then it's like a kind of a drag and drop, answer your own question, self-serve kind of system.
Yeah, this has been my exact experience too.
Yeah.
Hive came about as
exactly.
a function of people not wanting to write MapReduce tasks. So the problem that MapReduce has in practice, and why I don't think Google even uses it that much in the present day. This paper was written a while ago. We'll take a look at the publication date, but is that it's really hard to formulate your queries as map and reduce tasks.
But as I was saying earlier, if you think about what computer science is, it's all just abstractions built on top of abstractions. So
for sure,
like this abstraction came about and it was like very new at the time and people kind of went all in, and then people realized we actually need to abstract this. Like this is, 8 lines of code, but it needs even further abstraction. And so people built query languages on top of it and kind of moved on.
Well, I got super into this topic several years ago. Never took this class, never took a distributed computing class. However, there was a few innovations a few years back along the lines of what you're describing, which is the MapReduce paradigm of writing queries is not very human friendly or business friendly. And one of the innovations that's happened since is the creation of parallel relational databases. So Redshift is one example, Amazon's parallelized SQL database, which is optimized for reads. So a lot of the complaints that drove the development of MapReduce as an option for querying huge amounts of data is the speed of the queries. And two things that Redshift solved about that, and are along the lines of everything that's showing up in these lecture notes, are that one, you can scale out to n servers and achieve a factor of n reduction in runtime. And the other is to store your data in a read optimized way in a columnar oriented database, where traditionally databases store data in row oriented fashion, which for indexing, it makes it easier to write in single rows of data to a disk, but reading an entire column from a table requires seeking, not randomly, but seeking over a disk.
Definitely.
So if you have a table with 4 columns of the same data type, and you only want to read the first column, then that reading from column 1 to get a count of rows with a certain value is going to be 4 times more expensive than if that data was stored as a column continuously in memory or in disk on disk. So the innovations that kind of made this subject matter a little less attractive to learn are that people have learned to store their data in a column oriented fashion and to use SQL to provide businesses an easier way to get at the types of queries that this course is describing, the reasons MapReduce came about.
So in the conclusion it says MapReduce single-handedly made big cluster computation possible. So I do believe that before MapReduce came on the scene, or before Hadoop really came on the scene, like having the ability to store data and analyze it, in a distributed way, like didn't really exist in a way that was accessible to people. So it kind of changed the game there. And then I think through years of using it, it hasn't been the most efficient or flexible, but it was very powerful and it was easy for programmers to understand. And so we saw an explosion of kind of abstractions build on top of it
Mm-hmm.
that wouldn't have existed today had I don't think MapReduce been there
For sure.
15 years ago. 10
Yeah,
years ago.
no. So there's a few proper nouns that are worth mentioning here. One is, well, obviously MapReduce or Hadoop, which was the open source project out of Yahoo that, while Google wrote this paper about MapReduce, Yahoo wrote an open source framework for people to run MapReduce jobs called Hadoop.
Yep.
And we've already mentioned it. You mentioned Hadoop file system, HDFS.
Yep.
And that was very, very popular in like the late 2000s.
Yep.
People have kind of moved on since then
Yes.
to the kind of solutions I was describing of parallel relational databases like Redshift. But Redshift is just one example, and it was actually a fork of Postgres. So Amazon acquired a company that had forked Postgres, the SQL database, to be parallelizable.
Yeah.
And that was just Amazon's offering, and why that was a very loud flash in the pan for Amazon is that they priced it super cheap.
Yeah.
And made it very easy to load data from S3, their file system, into Redshift.
Yep.
But another option, or another predecessor to Redshift was called Hadoop DB.
Mm-hmm.
And it didn't use Hadoop file system, I don't think, but it was similarly a fork of Postgres that parallelized in a similar fashion to mapping SQL queries.
Yep.
But to give people another option, if you hate Amazon, is Spanner, which is a relational database out of Google. Also, I think after the MapReduce innovations.
Yeah, and here at Checkr, we actually use Presto, which came out of Facebook, which is a SQL engine built on top of Hive, which is built on top of
Hadoop.
Hadoop. It is built on top of Hadoop, but it can talk to multiple things. For us, our data lives in S3, or you can build connectors to actually go to source data. But really, the value is that it's built on top of Hive, which is kind of managing the indexing and stuff for us.
Got it.
Yep.
Well, shit. Yeah. No. I mean, we're wrapped on this first lecture. MapReduce single-handedly made big cluster computation popular. True. Not the most efficient or flexible, as Ben said.
Yep.
Scales well. Yes.
Yep.
Easy to program. Failures in data movement are hidden. That is a nice abstraction, assuming it's true.
Yep.
These were good trade-offs in practice. We'll see some advanced successors later in the course. So, looking forward to that. Have fun with the lab. I hope so.
Yeah.
Read the paper, the lab. Well, let's open the paper real quick, and then we'll read the abstract, and then take a look at the lab, because the lab is probably more interesting than the paper at this point.
Yep.
For people who don't know who Jeff Dean is probably the most distinguished Google engineering employee. He's got his own, Google Images results page. Here he is, looking happy.
There he is, working on Google File System.
He's also very active on the TensorFlow project, which is the hot shit at Google right now. That's their deep learning framework, which has kind of beat out every other option at this point. I heard that some open source projects are shutting down because they have their intersection of features are too overlapping with TensorFlow, and TensorFlow is getting too much attention. So, that's Jeff Dean. Sanjay Gamawat. I don't know who that dude is, but let's take a look at him or her. Well, photos of him and Jeff Dean, so they're probably super cool, close buddies. Well, fuck LinkedIn. 3 answers. Who's Sanjay Gamawat? Oh, he's smiling there. He's a research scientist. He works with MapReduce and distributed systems. Research divisions. I don't know what DEC is, do you?
I don't know.
Got his PhD at MIT. The modified object buffer, a storage management technique for object-oriented databases. MongoDB is an object-oriented database.
Yeah,
right?
I guess it's kind of an object-oriented database.
Damn you, Dr. Gamawat. He was the author of iCal. Oh, interesting. Okay. Oh, it does not related to Apple's iCal. Okay. He's listed as Silicon Valley's top and best programmers. Way to go, man. Oh, and he's worked on Spanner and
Oh, wow.
Bigtable, and Google File System.
So he's touched a lot of systems at Google.
For sure, dude. Oh, Spanner. The reason Spanner is more interesting in some ways than Redshift is that Spanner is a fork of MySQL.
Okay.
Where Redshift is a fork of Postgres, Spanner is a fork of MySQL, and it is used to back the AdWords bidding engine.
Interesting. Okay.
So
it scales.
yeah. So I mean, I'm sure they cache the hell out of it, but when you go and search for something, the ads that are matched and shown on your search results page are back to using Spanner to query for PageRank, or not PageRank, a quality score.
Yep.
But whatever, irrelevant. Pure functions, RPCs, remote procedure calls. Let's check out this paper. Let's read that abstract. Wow, that's a long abstract. That's an abnormally long abstract. Usually they're one paragraph, but this is Google, so they don't give a fuck.
Listen to that.
MapReduce is a programming model and an associated implementation for processing and generating large data sets. Users specify a map function that processes a key value pair to generate a set of intermediate key value pairs. This is just covering ground we already know. That merges all intermediate values associated with the same intermediate key. Any real-world tasks are expressible in this model, as shown in the paper. So I think in the paper they go and they describe how to perform these common queries that you might want to do with data. For example, counting words in a document, or unique occurrences of words in a document.
I think it's right. Word count.
Yeah. So they hypothetically, one use case that Google might have had for using this was coming up with PageRank scores. So finding all of the reference counts of different websites to a given URL. Or web pages to a given URL.
Yep. I mean, if you think abstractly, it's the same thing as word count, except you're not counting words, you're just counting links to domains. Okay.
I think we're done with this paper.
All right.
Nah. Yeah, let's check out the lab. So how are we doing on time?
I think we're doing
good?
Okay, on time, yeah.
Want to go through to 11?
Yeah, let's do 11.
All right.
For all the viewers, we'll end at 11.
What up? We have a guest. How's it going?
Oops, here are viewers.
How's our audio? Are you able to hear us? Oh, they already left.
They left.
All right.
Okay.
So in the lab. All right. You want to take it?
Sure.
Cool.
Introduction. In this lab, you'll build a MapReduce library as an introduction to programming in Go and to building fault-tolerant systems. In this part, we'll write a simple MapReduce program. In the second part, you'll write a master that hands out tasks to MapReduce workers, handles failures of workers. The interface to the library and approach to fault tolerance is similar to the one described in the original MapReduce paper. Collaboration policy. We don't have a collaboration policy. Software, we assume that you know about software.
Yeah,
we'll use Go. Git and Go, yeah. We actually don't know about Go, but
we don't. No.
We'll figure it out.
Both of us have written like lines of code.
Yeah, well, yeah. This will be a learning experience in Go.
So it's important to note that you're using Go version 1.7.
1.7. Okay.
Okay. Git to get at the source code. Okay, we can clone that. That looks like it has the code for all of the different labs.
Oh yeah. Okay. Let's just clone this.
So, assuming we make some progress with this, I mean, the class is already over, so making our solutions open source is probably, or making them public is probably not a problem.
It's probably not a problem.
They can't sue us.
Yeah, they can't sue us. We can put it on GitHub or something.
So there's a make file. There's some source code. You know about the tree command?
I don't know about the tree command.
Tree? Let's see if you got it.
That's why I don't know about the tree
command. Do you have Homebrew installed?
I do, yeah.
So we can brew install tree. So tree is a really rad command line tool for instead of LSing a single directory, it'll show you the file system under a given path that you tell it. And you can also tell it, don't traverse more than this step.
Go only too deep or something.
Yeah, so we can take a look at that, but in the meanwhile, we can look at this. So we're probably, I think we're first starting with
the MapReduce, maybe?
MapReduce, probably, yeah. So a bunch of Go files. Here's the test file. We'll open this in the IDE in a second, but my guess is the labs, completing the lab entails getting all of these tests to pass.
Yep.
I don't know why that's taking so long.
Yeah, let's see.
We don't need to commit any changes or share how to do that.
Okay.
So the MapReduce implementation we give you has support for 2 modes of operation, sequential and distributed. In the former, the map and reduce tasks are executed one at a time. First, the first map task is executed to completion, then the second and the third.
Yep.
So it's non-parallel. So sequential and parallel.
Yep.
When all the map tasks have finished, the first reduce task is run, etc. This mode, while not very fast, is useful for debugging. Definitely.
Definitely.
Distributed mode runs many worker threads that first execute map tasks in parallel and then reduce tasks. This is much faster, but also harder to implement and debug for sure. Let's see what kind of number of cores we got and whatnot. I know you got to explicitly declare how many processors or how many processes your Go routines or your Go programs use.
Okay.
But the appeal of Go is that you can max out the number of cores you're using for a given Go program very easily.
Yep.
By just setting an environment variable.
Yeah, I think I have 2 cores.
Okay, cool. We don't need to work. That's premature optimization. Preamble, getting familiar with the source. Okay. The MapReduce package provides a simple MapReduce library. Applications should normally call distributed located in master.go to start a job. Okay.
Okay.
So to start with, we'll probably try running the MapReduce code using sequential. The code executes the job as follows. The application provides a number of input files, a map function, reduce function, and the number of reduce tasks. Okay. So a master is created with this. So it sounds like when we were discussing earlier about how you kind of want to keep your input file sizes smaller so that the tasks are more small, so you get better chunking.
Yep.
That's up to us in terms of input files, but
it's
probably up to MIT.
Yeah.
They're giving us the input files. A master is created with this knowledge. It starts on an RPC server, which is the rpc.go file, and waits for workers to register using the RPC call register. As tasks become available in steps 4 and 5, schedule decides how to assign those tasks to workers and how to handle worker failures. The master considers each input file to be one map task and calls doMap at least once for each map task. It does so either directly when using sequential or by issuing the doTask RPC to a worker.
Okay.
Each call to doMap reads the appropriate file, calls the map function on that file's contents, and writes the resulting key value pairs to MReduce intermediate files. So doMap hashes each key to pick the. Do you understand what it's referring to about key?
Yeah. So the map function takes in input and emits key value pairs.
Mm-hmm.
So in this case, the key will be hashed so that it's like it'll randomly assign a
intermediate file to be written to.
Yeah, exactly.
So in the word count example, it would be the word.
Yeah.
The word is the key.
Yep.
And then we'd hash that to MReduce integer. That is the file name or whatever.
Yep.
So there will be n times n files after all map tasks are done. Each file name contains a prefix, the map task number, and the reduce task number. If there are 2 map tasks and 3 reduce tasks, the map tasks will create these 6 intermediate files. Okay, I think I'm 98% caught up.
Okay.
So the Mr. TMP.xxx, I think that's the host name and stuff, blah, blah, blah.
Yeah.
Each worker must be able to read files written by any other worker, as well as the input files. Real deployments use distributed storage systems, such as Google File System, to allow this access. even though workers run on different machines. In this lab, you'll run all the workers on the same machine and use the local file system. Okay.
Yep.
The master next calls be reduced.
Reduce at least once for each task, for each reduce task. As with do map, it does so either directly or through a worker. The do reduce for reduce task R collects the rth intermediate file from each map task and calls the reduce function for each key that appears in those files. The reduce task produces and reduce result files.
Okay.
Okay.
So in the example of those output files above, we'd get Mr. Temp.xxx 0, 1, and 2.
Yep.
Yes.
The three reduce functions we have. The master sends a shutdown RPC to each of its workers and then shuts down its own RPC server.
Okay. Over the course of the following exercises, you'll have to write and modify the do map, do reduce, and schedule functions yourself. These are located in commonmap.go.
You will also have to write the MapReduce functions in wordcount.go. Okay.
Okay. You should not need to modify any other files, but reading them might be useful in order to understand how the other methods fit.
Okay. So maybe we should just open up this directory.
Cool.
Let's see, what does makefile have?
Woo. Okay.
All right, makefile.
Oh, so you just say make lab 1 or whatever.
I think so, yeah. Make lab 1.
You need an API key. What is the API key used for? I'm worried that it might be submitting our source code to like a MIT server, and we need an API key to their MIT server.
Oh, hand in.
Yeah, we're not going to do that. We're going to run tests ourselves, and I'm pretty confident that's easy to do.
Well, I don't know. Let's try to do make lab.
Make lab 1.
Make lab 1. Let's see what we get.
Yeah, we don't have an API key, but otherwise it worked. So all it's doing.
Oh, all it's doing is just turning
zipping that in.
Okay, so it's not really doing very much. Okay, so we don't need makefile.
Yeah. My guess is that there's a way, once we have Go running on our laptop, we can run Go run test or something like that.
Okay.
And it'll run the tests in this test file.
Okay.
Similar to how most unit test frameworks works. So it should detect that the file name has test in its file name, and that there's functions with test in their name, and they'll just run those.
Cool.
Let's take another look at the lab real quick, because I think the lab's part 1, part 2, etc. So yeah, you receive credit for this lab if your software passes the tests. Oh, and they give the example of how to run the tests. So Go needs Go path to be set to the project's working directory. So we'll need to, let's see.
We can just run that.
Let's see if we have Go. Oh, you do have Go. Let's see if we have Go path. And we do have Go path.
Oh.
So if
what version of Go do we have?
Go version 1.7. Perfect.
Okay, we're good.
Wow, man. Maybe you used Homebrew. Maybe you went to their website and installed a DMG.
Yeah, I've played with Go off and on for a while.
So they want us to CD to where we're at, which is the source code for the labs.
Yep.
They want us to export Go path to be the project root of all the source code.
Yep.
And then we can CD into MapReduce. Oops. So we can, tree never installed. Maybe it's because we have a different terminal session or something. Whatever. So yeah, we can see all of the source code. And let's try running the tests and see them all fail. Or that one looks like there's only one test. Oops, I misspelled it. Sequential. Yep, test fails. No such file or directory. So it looks like that's an input file.
Okay.
And we don't have the input file. Let's deal with it in a second.
Let's see. I The output did not show okay next to the task. Your implementation has bug in it. To give me more verbose output, set enable in common go. Okay. Here we go. The output did not show okay.
Okay.
Missing some pieces. Before we can write your first MapReduce function pair, you'll need to fix a sequential implementation. In particular, the code we give you is missing two crucial pieces. The function that divides up the output of a map task and the function that gathers all the inputs for a reduce task. These functions are carried out by doMap function
and the doReduce function. Okay. Oh, so there's comments that should give us guidance about it.
Yeah.
To help you determine if you've correctly implemented them, we've got the unit tests. To run the tests, that's what we tried doing.
Yep.
Well, let's take a look at the tests to see where it's trying to load these test files from.
Yep.
Because that's where it looks like our tests are choking.
Where do we run sequential? So I'm guessing.
What was the flag, or how is run tests?
So just run sequential.
Let's check out the help information on go run or go test.
Go test.
Go help test. Pipe it into less. Go test automatically automates testing the packages named by the import paths. Okay. Prints a summary of the test results in this format, followed by detailed output for each failed package.
Recompiles each package along lines with matching file. Something test.
Okay.
Okay. So we have one test file, so it must recompile this one.
Mm-hmm.
Okay.
The Go tool will ignore directory name test data.
Okay.
By default, Go tests need no argument. Go test needs no arguments. It compiles and tests the package with source in the current directory, including tests, and runs the tests.
Package is built on a temporary directory, so it does not interfere with the non-test installation.
Okay.
Okay.
Let's look for -run.
What did we do? -run. Okay.
Go -run. Wow, doesn't exist.
Doesn't exist. Okay.
Awesome. It also accepts flags that control execution of the test. These flags are also accessible by Go test. See Go help test flag for details. We might need to do Go help test flag.
Go help test flag.
One word.
Run.
-run. Run only this.
Okay.
For tests, the regular expression is split into smaller ones by the top level slash, where each must match the corresponding part of the test's identifier.
So it must be running this one?
Yeah.
And this one.
So any functions that start with tests and have sequential in their name.
Yeah, okay.
So it looks like it's only running one test when we run go test -run sequential.
Maybe it stops after the first failing test.
Yeah, there's probably a flag we can give it to say run all the tests instead of fail eagerly or fail on the first one encountered.
I don't know if I have to recompile everything to have debug enabled.
I think the go test command
will do it.
Recompiles automatically each time, since it compiles the stuff in the build into a temporary directory.
Okay.
Like it was describing.
Let's
What did the doc say about debugging enabled?
To set this to true, this was false.
What's the style guide warning here? And the constant initializer true is not a constant. What does that mean? I'll say. Where did it say that in the lab notes?
Oh, add V. I didn't add V.
Oh, did you add it to common.go or did you add it to the tests? I think you added the const in the test file, not common.go. Oh no, you did. You did totally. Excuse me. Oh, that's not very much more verbose.
That's not very verbose.
Okay.
Test sequential. Okay.
So it's running one test.
It's running one test.
Let's go back to the lab docs.
Okay.
Okay. We're missing some pieces. Blah 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 blah. Blah 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 blah. To run the tests for the sequential implementation, this is exactly what we did.
Maybe let's just try running this exact command right here.
Good idea. Well, I think
that's what we did, but
the go path is our project root. Yeah. So, same output.
Same thing.
If the output did not show OK next to the tests, your implementation has a bug in it. Okay,
that's
of
fair.
course.
That's fair.
You'll get more output. Okay. Okay. These are examples of tests passing.
Okay.
Part 2 is a single worded count. Now you'll implement word count. There's some projects, some input file names with path names of the form blah, 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 which you download from Project Gutenberg. We don't have that. That's part 2. It seems like the tests we have are failing immediately for the sequential tests because it's not able to read these files that we don't have yet.
Well, let's just go. Maybe let's just read the test and see what's going on.
Okay. The test failing is test sequential single. Oh, we need to go into the test file. So it instantiates this sequential MapReduce runner.
Yep.
It waits.
Yep.
I'm not sure what for. It checks these files.
Make inputs. So we must be making fake inputs
these test
here.
Files. Yeah.
Yep.
There you go. Looks like it creates these files, but the file name looks like it's different than what the test expects. I was expecting a file name like this. So this is probably an artifact of our mask is probably not defined yet. So we're not creating the intermediate files for the reduce tasks to pick up.
So we do have an input file here, so it is making. So for number.
Okay. So let's take a look at the sequential the sequential test runner.
Okay, so it just made a file.
I don't know if it made a file or if that came. Oh, it's creating a test input.
Yeah, it created a test input here. So now,
let's look for the sequential class definition or function.
Yeah.
So this is there's two functions, sequential and distributed.
Yep.
And well, it has a run invocation.
Yep.
So the do map function is what we're not implementing currently, or does not do anything. And why the test is failing is probably because we're not writing any output. from the do map.
Okay.
And I think the do map is defined in common map. Yep. Yep. So do map manages one map task. It reads one of the input files, calls
Oh, I see. Okay.
calls the user-defined map function, mapf, for that file's contents, and partitions the output into MapReduce intermediate files.
Yeah.
Okay.
Okay. So you'll need to write this function.
The intermediate output of map task is stored as multiple files, one per destination reduce task. The file name includes both the map task number and the reduce task number. Use the file name generated by reduce name as the intermediate file for reduce task R. Call ihash, see below, on each key. Mod and reduce to pick R for a key value pair. Okay. This is what we were talking about in the lecture notes before. Yep. So,
okay.
We can, to start with, we can just add some log statements to print what do map is receiving. How to funct.println or whatever looks like the go way to print.
I don't normally type on this keyboard.
Let's see if funct is, funct is not actually imported. I think we need a comma. I think we need a comma after funct. Yeah.
I don't know, maybe not. Okay.
Funct print ln. No suggestions. Print job name. And try running the tests again with verbose on. Yeah. Undefined. Oh, okay. We're making it somewhere. Where's? Progress. Let's go back to the tests to see where it functs. Print line. Maybe. Does it do any printing here? No, that's reading input. Oh, fprint f. Oh, that's printing the file handler. Probably.
Let's look at the debug. Print f.
Print f as opposed to print ln. We're used to Java.
Yeah.
Yeah.
Sure.
Where is it printing read? You see how it says read the file name? Read
days merge.
Yeah. Okay.
Output task is stored as multiple files. Mapf. It reads one of the input files in file. So let's just read this file. How do we read this file?
Well, at this point, we're not even sure yet whether the test is getting to this point.
Yeah. Okay. Okay.
Is there? How did you pull up the super duper search? One that searches across all files.
Yeah. Command Shift F.
Can we go to specific directory? Search in there?
I think so.
Nothing to show. The reason I was searching read is because I'm curious to find where this is getting outputted.
Okay. Let's
or even that.
Yeah. Let's just leave it in project.
Oof.
Okay.
Oh, there we go. So
this is in master.
Oh, okay. We're getting that far. And then it calls schedule map phase.
Is that the function we were just? No, we were going to do map.
What is map phase?
Map phase.
It looks like it's some kind of hash map. Oh, so let's add a. Do you mind if I drive for just a sec? I was going to add a print here. Print F.
F, yeah. I guess we could also call it debug, maybe?
Looping over map. It does not. Oh, no, it does. Looping over maps.
Oh, interesting.
I think we need to add our own.
Yeah, we need to add
character.
this here. Okay.
Maybe there's another way to add new line.
Oh, tests. Maybe that's what I... Did I print that?
Yeah. So we probably were printing it, but it just didn't have a new line.
Yeah, it didn't look like...
So let's add... I think it's double quotes. We need to have double quotes.
Wow. I don't know if we're going to be able to string concat like that.
Yeah. Let's see. Let's see about new print ln. I think you're right.
Print ln.
Not f. Uses the default formats for its operands and writes the standard output. Spaces are always added between operands, and a new line is appended. As opposed to printf, it just formats.
Okay, so print. Yeah, let's try print ln.
Yeah. So we got it right, but we just goofed. Freaking go, man. So we'll add print ln here instead of manually appending a new line character.
All right.
Woo -woo!
All right, making progress.
So we can probably remove this now. The problem that we're facing is just implementing the first.
So we do need to implement this one.
Yeah.
Okay.
So we can say job name. Just taking a while to guess it, but
let's give it a shot.
Might choke. So it didn't interpolate. It
just appended, which is fine.
Yeah. Cool.
Okay.
So we have a job name.
Job name test. All right. Okay.
Okay. So they pretty much tell us what we need to do.
Yeah. So it reads one of those. So do map. It's given a job name, map task number, which map. Let's. See what we got here. In file.
Looks like the file name.
Use. And then I'm probably not going to be able to print this out, but let's give it a try.
Yeah. It's probably going to be like a pointer. Okay. Yeah, it's a hexadecimal. Oh, yeah. Cool.
Okay, so we have the in file, which is the one we need to read.
The reduce task this will be handed off to, or the number of reduced tasks.
Yeah, so the reduced task, the number of reduced tasks, so we need to shard it, I think, to 1, which is just just 1. And then we need to call this function with the input of, or with the contents of this file as the input.
Okay, cool.
I think.
So we'll need to read from the in file and pass it to, or do our word counting.
Yeah.
Using mapf, which is the word counting function they're giving us. What's the first comment block above this one? You'll need to write this function. The intermediate output of a map task is stored as multiple files, 1 per destination reduced task. In our case, there's only 1 destination reduced task. The file name includes both the map task number and the reduced task number.
Okay.
Use the file generated by reduce name.
Oh, here we go. Okay, let's try that.
Okay. So that will just generate a file name for us to write a result.
Map task number, and then what is R?
R is nReduce, I believe.
Reduce task int, yeah. Reduce.
Well, nReduce is the number of files we are writing to. The number of intermediate files handing off to. And nReduce is the number of reduced tasks.
Gotcha.
So
that's the number of reduced tasks. We need to figure out a way to shard it. So this will end up being like 0 or 1.
Call ihash on each key, and then mod nReduce to pick R.
Okay.
Yeah. So instead of passing nReduce to reduce name,
the key we get back from map.
Yeah.
Or the keys that we get back from map.
No, we're instead of MReduce to get R, we're going to call iHash of
for each key. So okay, so here's what I think we got to do.
Okay.
Mapf is going to return an array of key value pairs.
Okay.
So we're going to need to map over the key value pairs returned from mapf, which will give us each key.
And then figure
for
out
each
what
of those,
file
yeah.
name.
But for
we
now,
will write
let's
to.
just do 0.
Yeah, sounds good to me.
Just to see what's what.
Yeah, what's your IDE doing there?
It's telling me that's what this
Variable. What all variables that are set to 0?
No, I think because it doesn't have a name, it's telling me that that's what it's called here.
Oh, okay. Oh, got it. All right, let's give this a shot. Let's see what it prints. YOLO.
YOLO.
1. Or whoa. Okay, got a test file name. Or reduce.
Okay.
An intermediate file name to write
so
our MapReduce.
It wanted to open this one, but we got this one.
Well, no, I mean the merge the open mrtmp Mr. Temp.
Yeah.
Or MapReduce temp folder .test.
Yeah.
This is the test checking the final results of our MapReduce. So if we go check out
results.
the test
got
that's failing,
got it. You're right.
The test that's failing is this test sequential single.
I see.
Check worker is trying to see whether there's a final output file.
Yep, that makes sense.
Where we're seeing the test failure is trying to read a final file, which we're obviously not getting to because our doMap function is not writing any results.
I see.
That the doReduce function can.
That makes sense. Okay.
So
making progress here.
Mapf is like you said, we're going to need to loop over the contents of our.
Yeah. Let's get the
info.
contents first.
Oof, this is gonna be rough. We're gonna need to learn Go in like 6 minutes.
Okay, let's do this. All right, let's do it.
This is so much more brutal than like, for whatever reason, it's just way more complicated than, I mean, for good reason, it's way more complicated than reading files and reading lines from files in Python or Ruby or JavaScript or whatever, more dynamic languages. Okay, IOUtil.
Yes, okay.
Easy.
Easy. You can do this all day.
Before we, we need to import IOUtil.
You can do this all day.
We probably want to print content. So content may not be just a simple string.
Yeah, it's probably going to be some kind of binary.
Or a generator or iterator type of object where we'll need to read out the contents in chunks or flush it all.
Oh, well, here it says file
contents.
Oh, like maybe.
There's probably IOUtil read file, and there's probably IOUtil open file. And open file will return a pointer to the contents.
File, yeah.
But let's get this done. Might print out a ton. Oh, it didn't.
Undefined.
Undefined. Oh, we didn't add log.
Oh, no. Does that mean we got an error?
Yeah. Okay. Cool.
Oh, there we go.
Just print out the whole freaking contents of the info file.
Cool.
Cool. So now we can loop over it?
So I think what we do is we just give this content to mapf.
Yep.
So,
or do we?
So it says file string. Oh yeah. So we call. I think we call file.
Just content, or do we need
file
to pass
string? So
that's maybe the file name, in file and content. So what is mapf? I mean, it's our map function.
It's a map function.
Should it only take in one row, or maybe the file string argument is the file that should be written out to? So our reduce name. So maybe we need to get a reduce name.
I think this takes the file that it's input into for some reason.
How would we traverse up the call stack to see where doMap is invoked so we can see what mapf is? I think it's in master.go for the sequential MapReduce runner. It's getting mapf, and mapf is passed in when instantiating sequential. So sequential is called in the test. If we go over to the test and we look at what argument is being mapfunc, which is probably defined somewhere in this file.
Okay.
There we go. So it takes a string and
File string.
a file.
I think it's just the string.
What does that get used for? File?
I don't think it's getting used.
Is it getting used anywhere? It just doesn't get used for anything. Okay. All right. So it doesn't matter what we pass in there.
Let's try to.
Yeah. It looks like it's looping over the rows and the contents of a file, like you said, rather than taking a single row in a file. I don't know what strings.fields is doing, but let's hope that's what it's doing.
What is
result?
Yeah, where does that get defined?
So this is a return
it's passed
value.
in.
So Go is strange. And then,
it's defined ahead of time up there?
Yeah, so Go being type safe, you need to specify the types of your arguments into a function, but also the types of your return value.
I see.
So res is the variable name.
Yep.
And this brackets indicates that it's going to be an array or list of key values pairs, like you were describing.
Oh, and we define our key value pair in common.
Yeah.
Okay. That's kind of cool. Okay.
All right.
I think we're making progress.
Sweet. All right.
Okay.
So, like you were saying in commonmap.go, where we're defining our do map, we are invoking mapf on.
So this is going to be an array of key value. I don't really know how to.
I think we can just specify result. All right, result equals. We don't need to. We don't need to declare. I don't think we need to declare results type.
Because it's inferred.
Yeah. For example, up here, content, error. What's interesting is that colon equal syntax. And I think colon equal is important. Reason being, colon equal is a shortcut for saying automatically create these variables that we're declaring right here.
Yeah, and infer the type, I'm guessing.
Exactly.
Mapf is strict about what type is returned.
Exactly. So
so now it's complaining because we're just not using it.
Exactly. So let's try printing it. I think the result will be an array of key value pairs.
Yeah.
And we can loop over those to pass into our reduce intermediate file.
Yep. Give this a shot.
Not use content type as type string in argument to mapf. Okay. So we're not passing in an appropriate argument into mapf.
Okay. Let's
probably infile. Is infile a string?
Let's just try it. Let's see which one. I don't know which. Okay. Let's stop putting that. Okay, so I think it was this one that was not a string.
Yeah.
So I'm wondering how we can
check the type of a variable.
Yeah, or convert it to a string. Or what is this? Maybe this will tell us what this returns.
I think we just had it open. So it returns bytes.
An array of bytes.
So it's not a string for sure. However, if you printf it, it works.
Yeah, so
printf takes bytes. So convert printf to, or convert a string of bytes to a string. Or sorry, not string of bytes, a list of bytes to a string.
I'm sorry?
How to convert list of bytes to string. Yep. They're talking about massively performance stuff. Oh, that looks right.
Looks easy.
Do we need :n though? That looks like you only want to read up to a specific number of bytes. We want to just flush the whole string of bytes to the whole list of bytes to a string.
Yeah. If for some reason you don't have n, you could use a byte package to find it, assuming your input doesn't have a null character in it.
Or, as Ixa pointed out, you can use the code below. We might need to also import bytes,
yep,
which I think is a standard library thing. So we definitely don't want to depend on other external third-party code. We got to import it up top, I'm guessing.
I think my IDE is just complaining because I don't have it fully set up right.
But when we run Go on the command line,
it'll
work. Type int as type string in our, we're calling that after we call mapf, I think. We need to move that. Did you save the file? No. We're calling maybe.
I'm sorry. So it cannot use bytes index type content 0.
That's returning an integer?
As type string.
I know what's up. Mind if I drive for a second?
Yep, of course.
So what's going on is that this is a number of bytes, and we need to then call this on content.
I see.
Num bytes, and then we can pass s in. So if we were to print ln s, that'll print the contents of the file.
Let's print num bytes just to see.
It looks like camel case is the preferred.
Yes.
Undefined. We gotta do the colon equal. Freaking go, man.
All right, okay.
Panic. Ooh.
Slice bounds out of range.
Okay, we're probably doing this. It's a -1. Not good. Number of bytes -1. What is going on there? Maybe you couldn't find a file or something.
Let's go back to the and let's continue reading down. Maybe there's like a better way, like just this.
We can just
do string. Like,
yeah, I don't think we need to do this garbage. Yeah, let's just freaking.
Let's comment out this stuff.
Let's try doing that.
Okay.
Bytes. Where's that variable? Line 8.
Import not used.
Interesting that they complain about that.
Interesting.
So we are getting.
My
God!
We're making progress here.
We're getting back the array of key value pairs.
Progress.
Although we're not getting any values, it looks like we're just getting keys.
Okay.
So making progress for sure. So we finally figured out how to pass in the right content type.
Turns out you just wrap it in string function.
Yeah. So is there a way? So what's the type of results that we're getting back? If we look at mapf,
yeah,
it was defined in tests. Mapfunc here.
It returns a key value.
Key value, which looks like this this custom type key value.
Yep. You could command click it.
Sure. Which is key and value. So maybe we can get the first result returned. So print the first result.
Say more. Where did we define? Maybe we don't need to print the value. That's a long list. Let's keep printing the value. Yeah, I don't know how to loop over this.
Well, we can just print result 0
Okay.
and see what results 0 looks like.
Sure.
We should get a little less aggro results. So 0, 0. Okay.
Okay. Let's try to call dot value on that. And dot key.
All right.
So the key is 0, no value.
Okay.
Which I think is okay. So if we look at our test, split in words, we're just.
Why is it? Oh,
yeah. So
map is just counting the. Credits.
Yeah. So what we're going to do in reduce is not look at the value at all. We're just going to look at the count that we get.
Got it.
And it looks like that's not implemented yet.
Let's take another look at this comment here about what we do now that we've read the contents of our input file and have invoked the map function on that input file. So mapf, which is what which took us a little bit of a while to figure out how to even invoke, is the map function provided by the application. The first argument should be the input file name, coup, though the map function typically ignores it, which we found to be the case.
Yep.
The second argument should be the entire input file contents.
Yep.
Also, we figured out.
Yep.
Mapf returns a slice, whatever that means. It's a Go specific data structure containing the key value pairs for reduce. See common.go for the definition of key value.
Okay.
We did that.
Yep.
Look at Go's IUtil and OS packages for functions to read and write files.
Okay.
We did that.
Made progress.
Coming up with a scheme for how to format the key value pairs on disk can be tricky, especially when taking into account that both keys and values could contain new lines, quotes, and any other character you can think of. God, I hope we don't have to deal with that.
So sorry. Coming up with a scheme for how to format the key value pairs on disk can be tricky, especially when taking into account that both values. Okay.
So I'm guessing that is not an issue we're dealing with.
Yeah, I think
they're warning us that if we tried using this on our own input files, that we're going to run into all kinds of problems, as we're going to be working with documents or even parsed words that have extraneous characters like new lines.
I think they're telling us that, well, it's up to us to come up with a format for storing the intermediate results.
Mm-hmm.
And in this case, they're saying we could use JSON. So here we're getting back. Well, we don't know what the results look, or we don't know how our internal representation of the results will look yet, but we should just be able to convert those to JSON and then read them back in our do reduce function.
So they're giving us guidance about how we should store
I think so.
The data in the intermediate format?
Often used for serializing data to a byte stream that the other end can correctly reconstruct as JSON.
You're not required to use JSON, but as the output of the reduced tasks must be JSON, so the final step, familiarizing yourself with it here may prove useful. Okay. Yeah. You can write out a data structure as a JSON string to a file using the commented code below. Oh, that's very nice of them.
Yeah.
The corresponding decoding functions can be found in commonreduce.go. Remember to close the file after you've written all the values. Okay.
Okay.
So we're going to need to invoke that for every result.
Yeah, so I think, so what it said that we need to call iHash. So we need to generate the file name as an intermediate file for the reduced task.
So on line 36, we've already figured out how to invoke reduce name to get the file name that we should be writing any given mapf output to.
So we need to do like
for
result in
results.
I don't know the syntax.
We can. Are there examples? I think we've seen some examples of for loops, like in the map function, mapf definition in test, or test. I think the sequence. Yeah.
Oh, here
map func. So it's unclear what it's looping over.
Yeah.
But so
For unused.
results. I think you had it right before. I don't think there's any unused in this.
Oh, this key value. Or
It's an array, or what they call a slice.
so is that? What, I don't know what. I don't know what range it turns.
Word, or what words is defined to be.
Yeah. Let's
well,
here, let's just see.
We know. Well, we can look at mapf to see. Mapf is a slice. Maybe we can Google about Golang loop over slice. Iterating over slices. Blah 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 blah. Slices are used everywhere. Good to know. Blah blah blah. Oh my god. So this looks kind of like our key value struct.
Oh, I see. So a slice is a way to describe an array of.
So this is an array
things.
of dogs.
Yeah.
So the key here looks to be.
For some reason, we're just not using it. It must be something. Oh, maybe it's the index.
Yeah, totally. You're totally right. So yeah, that's why we use range. This is the counter of what the results
which we don't care about in this case.
We'll make it a little more explicit. But what we're going to do is we're going to get intermediate reduce file name, and we're going to set that equal to the reduce name. We're going to give it job name, map task number, and also we were looking at it. I forget what we were seeing. Control click, you said?
Yeah.
Or command click?
Command click.
So it takes a reduce task int. That's the ihash. We gotta call ihash.
Yeah.
So we're gonna call ihash of something.
Wait, no, undo that.
Ooh, I did in the wrong place.
Yeah.
Right.
So let's so this is the R. So ihash.
R equals ihash of
the key, I think.
Where did it say ihash? Call ihash on each key mod and reduce. So result.key mod and reduce.
Let's see. Hash takes just a string and returns an int. So I think it's. I think.
Oh yeah, no, I think you're totally right. Yep. And then we pass in that R to the intermediate.
So in our case, it's just always going to be 0 or 1 because we only have one reducer.
Yeah.
But hypothetically, if we had more, it would a round robin or randomly assign it to.
So let's real quick because it looks like I got this wrong. I'm using the Python syntax for mod.
Oh,
let's do Golang modulo, integer modulo. Math.mod. Looks like there's not a built-in syntax.
Yeah, I guess we need math.mod.
So we're gonna need to add math up here. And then call math.mod on the result of ihash and reduce.
Yep.
So we're gonna write our JSON to the given, not just write, we're going to want to append the JSON because we don't want to write over that file every time because there will definitely be more than one key being written to this intermediate file. And for that, we're going to be definitely doing what they recommend with regards to encoding the key value file or the key value variable.
So new encoder for key value. I'm not sure what we need to do there.
Yeah, dude, we've made it pretty far.
We made pretty good progress.
Do you want to call it a day? Or at least
sure.
a break for
yeah,
sure.
we could do a break.
Okay, well, let's switch back over to the live thing real quick. and close out because we're going to need to do something to share to YouTube if we want to do that.
Okay. All right. Are we done? Yeah.
Yeah, we're done for today.
This was fun.
We've been at it for like 2 hours
2
now.
hours, yeah.
Yeah, if you guys are curious, if you guys want us to do more of these, I don't know. We'll discuss.
We'll discuss
offline about whether the format works for us.
Yeah.
But cool.
Cool. See you guys.
Stop broadcast.